Hello everybody and welcome to Gravitational Fields Lesson 2. In the first video we looked at Newton's gravitational law. Newton's gravitational law looks at the gravitational force between two objects. And the equation is F, obviously the force is negative. Remember that we explicitly state the negative sign because we know that that force will always be attractive. So minus g, with g being the universal constant of gravitation, multiplied by mm. So the two m's are the masses of the two objects between which we're looking at the force, or between which the force acts, and divided by r squared, r being the separation from the centres of mass of the two objects. We also pointed out that Newton's gravitational law is an inverse square law, and we've seen at least a couple of examples of inverse square laws as part of year 2 at A level. So if we go from R and double it, then the force will become a quarter of that value. If we move out to 3r, then the force becomes a ninth of the value, and so on and so forth. What we're going to move on to now are Kepler's laws of gravitational motion. Now, just to give you a bit of historical context first, Kepler, or Johannes Kepler, was a German mathematician and astronomer, and he formed what we're about to see as his 3 laws of gravitational motion. Now, quite remarkably, Kepler himself didn't actually, so here is Kepler, didn't actually do any observation or any data taking by himself. He worked with a guy called Tycho Brahe. Now, Brahe was a Danish astronomer, and remarkably, Tycho Brahe took all of his measurements without the use of a telescope. Now, to me, that seems absolutely remarkable. The fact that Tycho Brahe did a load of measurements without the use of a telescope, which astronomers nowadays wouldn't even dream to do any kind of measurements without the use of a telescope or some kind of scientific equipment along those lines. What Kepler then did is he took the data that Brahe took, and he then formed 3 laws of planetary motion, which later on would prove to be absolutely correct. Now, Kepler and Brahe worked together. They did most of their work, or Brahe did most of his work and most of his measurements in the late 16th century, whereas Kepler did a lot of his work in the early 17th century. After that, we know that we had Newton come along, and Newton did most of his work in the late 17th century. Just to give you a couple of dates, Kepler actually died in 1630, whereas Newton was born in 1642. So Kepler died 12 years before Newton was even born, so there was actually no crossover between the two. And it was fascinating that Newton took, or at least the ideas of Kepler's laws of planetary motion, and then managed to later on, sort of 40-50 years after Kepler came up with his laws, managed to then turn around and prove them from his own mathematical point of view with his own theories. Now, at this point, I will be perfectly honest with you. There are 3 laws of planetary motion, so Kepler's 3 laws that we are going to look at. Realistically, from the syllabus point of view, we only really need to know and understand Kepler's 3rd law. But of course, the way that these laws are often formulated, unless we know, or at least have an idea of what the first law and the second law say, we're going to miss vital bits of information for the third law. So in this video, what we're going to do is we're going to have a look at Kepler's first law and second law, which, as I said, are ever so slightly beyond what we need to do for the syllabus for A-level physics. But of course, if we can get an understanding of what the first law and the second law say, when we come on to Kepler's third law, which we will do in the next video, we'll have a better idea of what the third law does really say. So going through this logically then, we'll do obviously Kepler's first law first. There you can see the definition on the screen. Kepler's first law, which is also known as the law of orbits, states that all planets move in elliptical orbits with the Sun at one focus. Now where it says elliptical orbits, that just means the orbit of the planet is the shape of an ellipse. There on the screen for you then is the shape of an ellipse. Now some people would call it an oval shape, which is probably the wrong word for it. Really an ellipse is just a squashed circle, and actually what I'll do in a few moments time is I'll show you really that the circle can just be considered as the special case of an ellipse. Now I've just added a couple of lines to the ellipse. The red line you see joins the 2 points on the ellipse that are the furthest away from each other. That line then is known as the major axis. The blue line we can see is the line that joins the 2 closest points on the ellipse, and hopefully we can guess very easily that that one is known as the minor axis. You can also see that the major axis and the minor axis cross each other at right angles. So those 2 axes are perpendicular to each other. Next then, we need to add 2 points on the major axis. So I'm going to do those in green. There's one there and there's one there. Now these 2 points are equidistant from that central point. So if you look at the point, I'll just mark it in with a black dot at the centre. If you look at that point there, which is where the minor axis and the major axis cross, the 2 green dots are equidistant from that. So the whole thing does work out symmetrical. I'm just going to label those with a capital F. And they are known as focal points. Singularly, they can be called a focus, and the plural of focus is foci. Now, one property of an ellipse is that if you choose any point on the ellipse itself and draw 2 lines, get rid of that one, from the focal point to the point on the ellipse, I'll label that one A and I'll label that one B. Then one of the properties of an ellipse is that when you add those 2 lengths together, A plus B will always equal a constant. Now one way, going way back to when I studied ellipses, one way that I was taught how to draw an ellipse is that if you just get a bit of string, and the bit of string would represent the 2 green lines that we've drawn, and just use a bit of blue tack or drawing pins or something like that to keep them fixed on the piece of paper, obviously at the 2 focal points. And then if you pull the string tight with a pen or a pencil and draw round while that string is tight, that will give you an ellipse. Now obviously when it comes to ellipses there has to be some way that we can measure how elliptical an ellipse is. You can have some ellipses which are really quite squashed and some ellipses which are getting close to being a circle, and that's known as, or that measurement is known as eccentricity. And let me just show you how we can measure that. So firstly, I'll do this in green actually, firstly I'm just going to define this distance here, which you can see is half of the major axis and is known as therefore the semi-major axis. I'm going to define that as a distance x. I'm then going to look at how far the focus is from the centre. So we're going to define that distance there as e times x. So the semi-major axis is x, and then e is our eccentricity. So we can see that as e increases, that distance e multiplied by x also increases, and the two foci become further and further from the centre of the ellipse, making it more elliptical. So if we have a small eccentricity, that implies it's getting closer to a circle, so it's more circular. And for a large e, we become more elliptical. Now if we go further with this eccentricity, let's look at the numbers that it could potentially be. Firstly, let's take the case where e is equal to 0. Well, if e is equal to 0, then this line e multiplied by x that we've just drawn, well, it doesn't really exist anymore. What happens at that point is that the two focal points, f and f, both end up at the centre of the ellipse. And well, if the two foci end up on top of each other, the major axis and the minor axis then become the same length, and we simply know that as a circle. Obviously, when we get greater than 0, and if we keep it less than 1, those are our conditions for an ellipse. So for an ellipse, the eccentricity has to be between, and you notice the use of my inequalities here as well, has to be between but not equal to 0 or 1. What that does is it keeps our line e times x less than x, which is the semi-major axis in the first place. Now, going a little bit further, and this is probably way beyond what we need to worry about today, but if e is equal to 1, we end up with special cases, and that's known as a parabola. And even if we get e to be greater than 1, that is known as a hyperbola. But as I said, parabola and hyperbola are way beyond what we need to do as part of A-level physics. In maths and probably further maths as well, you'll explore parabolas and hyperbolas, and especially if you go on to higher level maths learning, you'll look at those. I just thought I'd let you know, but like I said, that's way beyond what we need to worry about at the moment. Now, just to give you an idea of the kind of eccentricities that we have in our solar system, for Earth, we might as well do Earth first. For Earth, the eccentricity is 0.0167. Now, you can see that that is an incredibly small number in the grand scheme of things. If we're defining an eccentricity for an ellipse to be anywhere between 0 and 1, to have an eccentricity of 0.0167, so less than 0.02, shows you that the Earth's orbit is fairly circular. Yes, okay, it is elliptical. It is a little bit elliptical, but it's not massively elliptical. It's far closer to being a circle than it is to being sort of really quite elliptical or anything like that. Now, in our solar system, our orbit, Earth's orbit, isn't the least elliptical that we have. Venus actually has the least elliptical orbit, where E is 0.0068. So again, a very small eccentricity for Venus. Venus is the smallest, Neptune is next smallest, and Earth has the third smallest eccentricity out of the planets that orbit the Sun. In fact, when we look at the 8 planets, all of them, apart from one, have an eccentricity less than 0.1. The largest eccentricity of the planets is Mercury, which has an eccentricity of 0.206. So Mercury has got quite an elliptical orbit, but the rest of the planets have really quite circular orbits. So that's Kepler's first law then. All planets move in elliptical orbits with the Sun at one focus. So the last thing that we just need to do is to say that, well, we've got 2 foci, and for each planet, the Sun will sit at one of those foci. Next then is Kepler's second law, and Kepler's second law, you can see, is also known as the law of areas, and states that a line that connects a planet to the Sun sweeps out equal areas in equal times. So here now, just to bring the first law forward, here's our ellipse. I've only drawn the major axis in, but I've put the Sun at one focus. The other focal point would be probably about there, but we don't necessarily need to worry about that right now. So let's have a look at the second law. So a line that connects the planet to the Sun. Well, let's draw over here a couple of points. So let's have point A and point B. And let's join point A to the Sun and join point B to the Sun. Now we can see that those lines have given us an area which is not too dissimilar to a triangle, but at least it's given us some kind of area. What I'm going to do is exactly the same over here. So I'm going to have point C and I'm going to have point D. Do the Sun to point C, and I'll do the Sun. They should be straight lines. In fact, let's try those again. No, not much better. Okay, fine. That'll have to do for straight lines. We've got another area there. So I've drawn out now 2 areas. We're obviously assuming at the moment that the planet is moving in that direction. Now, what the second law says is that when the planet moves from A to B, if it takes a certain time, delta t, and if it moves from point C to D, if that time period between point C and point D is the same as the time period between point A and point B, then those 2 shaded areas, the green shaded area and the blue shaded area, will be the same. It's interesting then to look at what the implications of Kepler's second law are. Now, I know that the ellipse I've drawn, and I've drawn it slightly exaggerated, but hopefully it will make the point. We can see that points A and B are closer to the Sun than points C and D. Now, with A and B being closer to the Sun, the 2 green lines that I've drawn in here must be shorter than the 2 blue lines. So the lines from the Sun to A and B are shorter than the lines from the Sun to point C and D. Therefore, in order to keep these 2 shapes the same size, this distance here between point A and point B, which using maths terminology is the line AB, has got to be bigger than the line joining C and D. So AB has got to be greater than CD. The distance from A to B greater than the distance from C to D. Now that's distance. If we now relate that to velocity, relate it to speed, because this distance is the same, because A times B, is greater than C times D, when we divide those by the time, in order to turn it into a velocity, we can see that the velocity between A and B must now be greater than the velocity between C and D. The time periods are both exactly the same, but the distances are larger, and therefore the velocity must be larger as well. Moving that on further, again, if we go back to what we were saying a moment ago about the eccentricities, when you've got something like the Earth, which is 0.0167, relatively circular orbit, the difference in velocities at different points on the orbit is going to be very small. However, as you increase the eccentricity, we find that those differences in velocities become more pronounced. And with hopefully a little bit of logic, we can see that an object, whether it be a planet or obviously moving up to a comet or something like that, will be moving fastest when it is at the closest point to the Sun, which is at that end of the major axis. And conversely, it will be moving slowest at that point furthest away from the Sun at that end of the major axis. Now those 2 points do have technical names. This point here is known as Perihelion. Now you'll notice that we've got the word helion there, which comes from the word helios, which is the Greek word for the Sun. Over here then we have the aphelion. Okay, notice the pronunciation there, it's called the aphelion. Don't try and anglicise it and say aphelion. We've obviously, as we said, we've got that word helios there, which means sun, and helion is derived from that. So we have the perihelion, closest point to the Sun, and we have the aphelion, furthest point away from the Sun. Just to finish the terminology there, the word peri in Greek denotes near, and the word ap actually comes from apo in Greek, which means away from. Now, just to give you a bit of context, normally on the Earth's orbit, we reach perihelion on approximately the 4th of January, and we reach aphelion on approximately the 4th of July. Now that does vary. Perihelion can be anywhere from sort of the afternoon of the 2nd of January to the morning of the 5th of January, depending on many factors, obviously including where we are in our leap year cycle as well. But normally it falls on, or at least very close to, either the 4th of January for perihelion and the 4th of July for aphelion. Now obviously what we're saying is that at least in the northern hemisphere we're reaching our closest point to the Sun on the 4th of January, when in theory we're in the middle of our winter and it should be the coldest. Remember, the eccentricity is 0.0167, a very small eccentricity, especially when you compare it to the 23 degrees that the Earth's axis of orbit is tilted, compared to compared to the vertical, compared to our orbit around the sun. So a 23-degree difference on our axis of rotation compared to 0.01, less than a 2% difference compared to how close or how far away we are from the sun. So really, being closer to the sun, at least from the Earth's point of view, makes virtually no difference to our weather and to how warm or cold it is during our winter in the northern hemisphere, compared to the tilt of 23 degrees of our axis of orbit. Where we do see the big difference, though, is in comets. Now, comets have very large eccentricities. Some of them, for example, Halley's Comet, which is probably the most famous comet that most people will have heard of, has got a massive eccentricity. It has an orbit of around about 80 years. And the eccentricity of Halley's Comet is actually 0.97, so it's almost as elliptical as you can possibly get. So when it is at perihelion, it is moving very quickly, and it is also very close to the sun, whereas when it's at aphelion, it is quite a long way away. It's around about 17 times the distance from the Earth to the sun, so 17 or just short of 18 really astronomical units that Halley's Comet will get away from the sun when it's at aphelion. So to summarise then, in this video we've looked at the first two of the three laws of planetary motion, the three Kepler's laws of planetary motion. The first law, the law of orbits, states that all planets move in elliptical orbits with the sun at one focus. And the second law states that a line that connects a planet to the sun sweeps out equal areas in equal times, and as you can see, that one is known as the law of areas. So that's it for this video. Obviously, as I said earlier, in the next video, in Gravitational Fields 3, we will look at Kepler's third law, which again, as I said earlier, that's really what is part of the syllabus. What we looked at in this video is really just the sort of preamble to give us at least the grounding in the first two laws to help us to fully understand the third law. So as usual, thank you for watching, and I'll see you in the next video.